Hi, good day everyone. Today we're gonna discuss the uncertainty management in rule-based expert systems. So the topic that we're gonna tackle under uncertainty management in rule-based expert system are what is uncertainty, basic probability theory, Bayesian reasoning, bias of the Bayesian method, certainty factors theory, and evidential reasoning. What is uncertainty in expert systems? So according to Stefano and Sage in 1987, uncertainty can be defined as the lack of the exact knowledge that would enable us to reach a perfectly reliable conclusion. So basically, uncertainty refers to a situation where we do not have complete information. So kung uncertain po tayo, then we are not entirely sure about the outcome. However, classical logic permits only exact reasoning. It assumes that perfect knowledge always exists and the law of the excluded middle can always be applied. So, classical logic is a system of reasoning na nag-a-assume po ng every statement is either true or false and that there is no middle ground. So, it means po na kung ang isang statement ay true, then its negation or yung kabaliktaran niya must be false and vice versa. In other words, there is no third option, such as a statement being neither true or false. For example, if A is true, then A is not false, and if B is false, then B is not true. What are the sources of uncertain knowledge in expert systems? In general, we can identify four main sources, and those are weak implications, imprecise language, unknown data, and difficulty of combining the views of different experts. Weak implications. Rule-based expert systems often suffer from weak implications and vague associations. Domain experts and knowledge engineers have the painful and rather hopeless task of establishing concrete correlations between if and then parts of the rules. So, ang rule-based expert systems are not always able to make accurate predictions because the knowledge they are based on is often incomplete or imprecise. Ang problem po with the rule-based expert system is kung yung if part of the rules are often imprecise. So kagaya po na example last time, so during the pandemic period na if nilalagnat yung isang tao, then may COVID kaagad siya. When in fact is maraming dahilan kung bakit po siya nilalagnat. Therefore, expert systems need to have the ability to handle vague associations. For example, by accepting the degree of correlations as numerical certainty factors. Imprecise language. Our natural language is inherently ambiguous and imprecise. We describe facts with such terms as often and sometimes, frequently and hardly ever. As a result, it can be difficult to express knowledge in the precise if-then form of production rules. So ang mga words daw po na ginagamit po natin in our natural language can have multiple meanings or na-interpret po siya in different ways. For example po, yung word na often, para sa akin is meron siyang ibang meaning and then sa inyo po is meron po siyang ibang kahulugan. So this ambiguity can make it difficult to express knowledge in the precise if-then form of production rules. So for example, gamitin po natin yung word na often in a rule. If it often rains, then take an umbrella. Di ba naging ambiguous siya or malabong maintindihan dahil sa salitang often, which can have multiple meanings. However, if the meaning of the facts is quantified, it can be used in expert systems. For example po, pwede po tayong mag-assign na value na 0.9 to the fact, it often rains in Manila. So it means na we are 90% confident that it rains in Manila most of the time. And by quantifying the meaning of facts, we can make them more precise and easier for computers to understand. And in 1944, Ray Simpson asked 355 high school and college students to place 20 terms, like often on a scale between 1 and 100. And in 1968, Milton Hackle repeated this experiment. So the table 3.1 shows the quantification of ambiguous and imprecise terms on a time frequency scale, an experiment conducted by Ray Simpson in 1944 and by Milton Hackle in 1968. Unknown data. When the data is incomplete or missing, the only solution is to accept the value unknown and proceed to an approximate reasoning with this value. Combining the views of different experts. Large expert systems usually combine the knowledge and expertise of a number of experts. Experts have contradictory opinions and produce conflicting rules. So, to resolve the conflict, the knowledge engineer has to attach a weight to each expert and then calculate the composite conclusion. So, this weight refers to the degree of confidence. And the experts with higher weights are given more weight in the decision making process. No systematic method exists to obtain weights. So basically, the knowledge engineer has to rely on their own judgment to decide how much weight to give to each expert. An expert system should be able to manage uncertainties because any real world domain contains an exact knowledge and needs to cope with incomplete, inconsistent, or even missing data. A number of numeric and non-numeric methods have been developed to deal with uncertainty in rule-based expert systems, according to Batnagar and Canal in 1986. So, as what we have said in the introductory part, that we will tackle the most popular uncertainty management paradigms, which are the Bayesian reasoning and uncertainty factors. However, we will first look at the basic principles of basic probability theory. So the concept of probability has a long history that goes back thousands of years with words like probably, likely, maybe, perhaps, and possibly were introduced into spoken languages, according to Good in 1959. However, the mathematical theory of probability was formulated only in the 17th century. The probability of an event is the proportion of cases in which the event occurs. Probability can also be defined as a scientific measure of chance. And probability, probability can be expressed mathematically as a numerical index with a range between 0 and absolute impossibility to unity and absolute certainty. Most events have a probability index strictly between 0 and 1, which means that each event has at least two possible outcomes, which are the favorable outcome or success and unfavorable outcome or failure. The probability of success and failure can be determined by the probability of success is equals to the number of success divided by the number of possible outcomes, and the probability of failure is equals to the number of failures divided by the number of possible outcomes. So therefore, if S is the number of times success can occur, and if is the number of times failure can occur, then we can generate this equation where the probability of success is equals to P is equals to success divided by success plus failure, where success plus failure is the number of possible outcomes. And the probability of failure is equals to Q is equals to failure divided by success plus failure. And as we have observed, there are two letters, which are the P and Q, where P represents the probability of success and Q is the probability of failure. And then when we add these two values, their sum is equals to 1. Kung nagtataka po kayo kung bakit equals to 1, because the probability of success is 1/2 and the probability of failure is 1/2. So this satisfies the equation P plus Q is equals to 1. Kagaya po ng kanina, so sinasabi po nito na there are at least two possible outcomes since the success is equals to P and then F is equals to Q. Or the failure is represented by Q and then the success is represented by P. So P plus Q, we have 1. So example, If we throw a coin, the probability of getting a head will be equal to the probability of getting a tail. In a single throw, S is equals to F is equals to 1, and therefore, the probability of getting a head or a tail is 0.5. So, i-compute po natin kung bakit po 0.5 yung probability of getting a head or a tail. So, when we toss a coin daw po once, there are two possible outcomes, which is the probability of getting a head, which is equals to the probability of getting a tail. And the formula success is equals to failure is equals to 1 refers to the number of successful outcomes and the number of unsuccessful outcomes. So the value of S is equals to 1 and the value of F is equals to 1. So we have here the formula that calculates the probability of getting a success, which in this case is getting a head. So success is equals to 1 divided by 1 plus 1, which is the total number of outcomes. So P is equals to 1 divided by 2. So the probability is 0.5. So it means that there is a 50% chance of getting heads when you toss a coin once, and the probability of getting tails is also 50%. Conditional probability. Let A be an event in the world and B another event. Suppose that events A and B are not mutually exclusive. So not mutually exclusive means that they can both happen at the same time, but occur conditionally on the occurrence of the other. So it means that they can happen at the same time, but that one event cannot happen without the other event happening first. And the probability that event A will occur if event B occurs is called the conditional probability. So conditional probability refers to the measure of probability of an event occurring given that another event has already occurred. And conditional probability is denoted mathematically as conditional probability of event A occurring given that event B has occurred, in which the vertical bar, this one, represents given, tinatawag po siyang given, and the complete probability expression is interpreted as conditional probability of event A occurring given that event B has occurred. So we have here the equation, the expression for the conditional probability, where conditional probability of event A occurring given that event B has occurred is equals to the number of times A and B can occur divided by the number of times B can occur. So the number of times A and B can occur, or the probability that both A and B will occur, is called the joint probability. So joint probability refers to the probability of two or more events happening together, which in this case is events A and B. It is represented mathematically as probability of events A and B both occurring together. So the number of ways B can occur is the probability of B. So itong mathematical equation po na ito is derived from this expression, where this expression po, the probability of events A and B both occurring together is ito po, the number of times A and B can occur, and the probability of B is the number of times B can occur. And then, similarly, the conditional probability of event B occurring given that event A has occurred. So this equation represents the conditional probability of B given A, which is similar to the equation above. So nakita po natin na same lang po, but with A and B swap. So pinag-swap po yung A and B. So the probability of B given A is equals to the probability of events B and A occurring together divided by the probability A. Hence, so this equation simply rearranges the equation before. Ito po. Itong equation na to. So it shows that the joint probability of both events B and E happening can be found by multiplying the probability of event B given that event A has occurred multiplied by the probability of event A. The joint probability is commutative, thus, so it means po that the probability of A and B occurring together is the same as the probability of B and A occurring together. Therefore, probability of events A and B both occurring is equals to the probability of B given that event A has occurred multiplied by probability A. And then we'll substitute the last equation, this equation, into this equation. And then after substituting, it will yield into a Bayesian rule where the where probability where the conditional probability that event A occurs given that event B has occurred is equals to the conditional probability of event B occurring given that event A has occurred multiplied by probability of event A occurring divided by the probability of event B occurring. So the concept of conditional probability introduced so far considered that event A was dependent upon event B. This principle can be extended to event A being dependent on a number of mutually exclusive events B1, B2, up to Bn. The following set of equations can then be derived from the equation where A is always dependent upon event B. So when we combine this equation, it will yield into this one where the sum from I up to n of the joint probabilities of A and each event Bi is equals to the sum from I is equals to 1 up to n of the conditional probabilities of A given that each event Bi multiplied by the probabilities of those events Bi. So if the occurrence of event A depends on only two mutually exclusive events, so ang kanina po is not mutually, ngayon is two mutually exclusive events na, which means na if one event happen, then the other event cannot happen at the same time. So for this one is B and not B. So we have the probability A is equals to probability of A given B multiplied by probability of B plus probability of A given not B multiplied by probability not B, where this symbol is the logical function read as not. Similarly, probability B is equals to P of B given A multiplied by probability A plus P of B given not A multiplied by P not A. So nakita po natin is pinag-swap lang po dito yung A and B kagaya na ginawa kanina. And then this equation, we will substitute it into the Bayesian rule. So di ba po ito po yung Bayesian rule natin. Ito po. So we will yield into this equation where probability of A given B is equals to probability of B given A multiplied by probability A divided by probability of B given A multiplied by probability A plus probability of B given not A multiplied by probability not A. If in case na there are only two mutually exclusive events which are B and not B. So Bayesian reasoning. Suppose all rules in the knowledge base are represented in the following form. If E is true, then H is true with probability P. So kung yung last time lang po is if then statement lang ang meron, so ngayon is with probability P na siya. This rule implies that if E occurs, then the probability that event H will occur is P. In expert system, H usually represents hypothesis and E denotes evidence. So, yung last equation po natin is we will just rephrase it and we will replace B with E, which is the evidence, and A with H, which is the hypothesis, where probability of H given A is equals to probability of E given H, where The probability that hypothesis H being true will result in evidence E multiplied by prior probability H, where the prior probability of hypothesis H being true and then divided by probability of evidence given hypothesis multiplied by prior probability H plus probability of evidence given not hypothesis. So it is the probability of finding evidence E even when hypothesis H is false multiplied by probability of not H. It is the prior probability of hypothesis H being false. So in expert systems, the probabilities required to solve a problem are provided by experts. An expert determines the prior probabilities for possible hypothesis and probability not hypothesis, and also the conditional probabilities for observing evidence E if hypothesis H is true is probability of evidence given hypothesis, and if hypothesis H is false, so probability of evidence not hypothesis. Users provide information about the evidence observed and the expert system computes probability of hypothesis given evidence for hypothesis H in light of the user supply evidence. Probability of hypothesis given E is called the posterior probability of hypothesis H upon observing evidence E. So posterior probability represents the updated or revised probability of an event occurring after incorporating new information or evidence. So we can take into account both multiple hypotheses, hypothesis 1, hypothesis 2, hypothesis M, and multiple evidences, evidence 1, evidence 2, up to evidence N. But the hypothesis as well as the evidences must be mutually exclusive and exhaustive. So it means for mutually exclusive that the hypothesis and evidence cannot happen at the same time, and the hypothesis and evidence cover all the possible outcomes. So for the single evidence and multiple hypotheses, we could use this equation. And for the multiple evidences and multiple hypotheses, this equation can be used. However, this requires to obtain the conditional probabilities of all possible combinations of evidences for all hypotheses. This requirement places an enormous burden on the expert and makes his or her task practically impossible. Therefore, in expert systems, conditional independence among different evidences assumed. Thus, instead of unworkable, it was attained. So, to calculate the probability of each possible combination of evidence given each hypothesis, it is a very difficult task and time-consuming as there could be many possible combination of evidence and hypothesis. So to simplify the task of calculating the probabilities of different hypotheses given a set of evidences, the assumption is often made. So instead of those unworkable equation, they have attained this equation. So instead na ito po yung gamitin kasi po, it would take a longer process po kung ito po yung gagamitin. So to simplify it, this equation has been made. So ranking potentially through hypothesis. Let us consider a simple example. Suppose an expert, given three conditionally independent evidences, evidence 1, evidence 2, and evidence 3, creates three mutually exclusive and exhaustive hypotheses, hypothesis 1, hypothesis 2, and hypothesis 3, and provides prior probabilities for these hypotheses, probability hypothesis 1, probability of hypothesis 2, and probability of hypothesis 3, respectively. The expert also determines the conditional probabilities of observing each evidence for all possible hypotheses. Table 3.2 shows the prior and conditional probabilities, and we will assume that we first observe evidence, which is evidence 3. The expert system computes the posterior probabilities for all hypotheses. So now we will just look for the single evidence with multiple hypotheses. So we will use this equation. The probability of hypothesis I given evidence 3 is equals to the probability of evidence 3 given hypothesis I multiplied by prior probabilities of hypothesis I divided by the sum from k is equals to 1 up to 3 of the probability of evidence 3 given hypothesis k multiplied by probability of hypothesis k, where our I is 1, 2, 3. So we will start with our index I with 1. So the probability of hypothesis 1 given evidence 3 is equals to the probability of evidence 3 given hypothesis 1. So our I is equals to 1. So we have 0.6 multiplied by prior probability H1. So we have 0.40. And if we multiply them, their product is 0.24. So the sum from k is equals to 1 up to 3. So of the probabilities. So our index k is equals to 1. So our index k is equals to 1. So probability of evidence 3 given hypothesis 1. So we have our k is equals to 1. So we have 0.6. And then multiplied by probability of hypothesis 1. So we have 0.40 plus our index k now is equals to 2. So probability of evidence 3 given hypothesis 2. So our k now is 2. So we have 0.7 multiplied by probability of hypothesis 2. So we have 0.35 plus our index k now is equals to 3. So probability of evidence 3 given hypothesis 3. So our k is 3. We have 0.9 multiplied by prior probability hypothesis 3. We have 0.25. And then if we multiply them and then add their products, so the sum is 0.71. 0.24 divided by 0.71 results that the probability of hypothesis 1 given evidence 3 is 0.34. And our index I now is equals to 2. So the probability of hypothesis 2 given evidence 3 is equals to the probability of evidence 3 given hypothesis 2. So our I now is equals to 2. Evidence 3 given hypothesis 2, we have 0.7. And then the prior probability of hypothesis 2, which is 0.35. And then since same process lang naman po yung sa kanina, so we will just copy. And then if we multiply 0.7 by 0.35, their product is 0.245. 0.245 divided by 0.71 shows that probability of hypothesis 2 given evidence 3 is equals to 0.34. And our index I now is 3. So the probability of hypothesis 3 given evidence 3 is equals to probability of evidence 3 given hypothesis 3. So our I now is 3. So we have 0.9 multiplied by prior probability hypothesis 3. So we have 0.25 and then same process. So copy lang din natin para hindi po tayo matagalan. And 0.9 multiplied by 0.25, their product is 0.225. 0.225 divided by 0.71 shows that probability of hypothesis 3 given evidence 3 is equals to 0.32. So after observing po, it shows that with evidence 3, that hypothesis 1 and hypothesis 2 are the same. And while the hypothesis 3 is 0.32, so malapit-lapit lang po siya sa hypothesis 1 and hypothesis 2. Suppose now that we observe evidence 1, the posterior probabilities are calculated. So ngayon is nadagdagan po siya ng evidence 1. And then our index I is 1, 2, 3. So the probability of hypothesis I given evidence 1, evidence 3 is equals to probability of evidence 1 given hypothesis I multiplied by probability of evidence 3 given hypothesis I multiplied by prior probabilities of hypothesis I divided by the sum from k is equals to 1 up to 3 of the probabilities of evidence 1 given hypothesis k multiplied by probability of evidence 3 given hypothesis k multiplied by prior probabilities hypothesis k. So our index I is equals to 1. So the probability of hypothesis I given evidence 1, evidence 3 is equals to probabilities of evidence 1 given hypothesis 1. So our I is equals to 1. We have 0.3 multiplied by probability of evidence 3 given hypothesis 1. So we have 0.6 multiplied by prior probabilities hypothesis 1. So we have 0.40. And if we multiply them, their product is 0.072. And then our index k starts from 1. So our k, the value of k, so our k is equals to 1. So probability of evidence 1 given hypothesis 1. So our k is equals to 1. We have 0.3. And then multiplied by probability of evidence 3 given hypothesis 1. So evidence 3 and our case 1. So we have 0.6 multiplied by probability, prior probability H1. So we have 0.40 plus, and then our index k now is equals to 2. So the probability of evidence 1 given hypothesis 2, our case 2. So evidence 1, we have 0.8 multiplied by probability of evidence 3 given hypothesis 2. So we have 0.7. And then higher probability of hypothesis 2, we have 0.35. Plus, our index k now is 3. So 3 na. So prior probability of evidence 1 given hypothesis 3, since our k now is 3, so we have 0.5. And then multiplied by prior probabilities of evidence 1 given evidence 3 given hypothesis 3, so we have 0.9. And then multiplied by probability of hypothesis 3, so we have 0.25. And then if we add all the products, so the sum is 0.3805. So the answer is of the probability of hypothesis 1 given evidence 1 and 3 is 0.90. And then our index I now, is 2. So the probability of hypothesis 2 given evidence 1, evidence 3 is equals to probability of evidence 1 given hypothesis 2. So our I is equals to 2. Evidence 1 given hypothesis 2, we have 0.8 multiplied by probability of evidence 3 given hypothesis 2. So we have 0.7 multiplied by prior probability of hypothesis 2. So we have 0.35. And if we multiply them, their product is 0.196. And divided by 0.3805 is equals to 0.52. So our index I now is 3. So the probability of hypothesis 3 given evidence 1, evidence 3 is equals to probability of evidence 1 given hypothesis 3. Our I is equals to 3 now. So we have 0.5. And then probability of evidence 3 given hypothesis 3. So we have 0.9 multiplied by prior probability of hypothesis 3. So we have 0.25. And if we add all their product, if we multiply them, their product is 0.1125 divided by 0.3805. So the probability of hypothesis 3 given evidence 1, evidence 3 is 0.29. So after observing evidence 1, it shows that the hypothesis 1 has decreased drastically po from before, and the hypothesis 2 has increased while hypothesis 3 has also decreased. And after observing evidence 2 as well, the expert system calculates the final posterior probabilities for all the hypotheses. So the probability of hypothesis I given evidence 1, evidence 2, evidence 3 is equals to probability of evidence 1 given hypothesis I multiplied by probability of evidence 2 given hypothesis I multiplied by probability of evidence 3 given hypothesis I multiplied by prior probabilities of hypothesis I divided by the sum from k is equals to 1 up to 3 of the probabilities of evidence 1 given hypothesis k multiplied by probability of evidence 2 given hypothesis k multiplied by evidence 3 given hypothesis k multiplied by prior probabilities hypothesis k, where our I is equals to 1, 2, 3. So our index I starts from 1. So the probability of hypothesis 1 given evidence 1, evidence 2, and evidence 3 is equals to the probability of evidence 1 given hypothesis 1. So our I is equals to 1, and then the probability of evidence 1 given hypothesis 1 is 0.3 multiplied by probabilities of evidence 2 given hypothesis I, we have 0.9, and multiplied by probabilities of evidence 3 given hypothesis I, so we have 0.6. And then the prior probabilities of hypothesis 1 is 0.40. And then if we multiply them, their product is 0.0648. So the sum from k is equals to 1 up to 3. So our index k is equals to 1. So 1 po yung index k natin. So the probability of evidence 1 given hypothesis 1. So our k is 1. And then evidence 1, we have 0.3 times probability of evidence 2 given hypothesis 1. We have 0.9. And then multiplied by probability of evidence 3 given hypothesis 1. So we have 0.6. And then multiplied by prior probability H1. So we have 0.40 plus. So our K now, our index K is 2. So the probability of evidence 1, our K now is 2. So evidence 1 given hypothesis 2, we have 0.8. And then multiplied by prior probability, the probability of evidence 2 given hypothesis 2, we have 0.0. Multiplied by probability evidence 3 given hypothesis 2, we have 0.7. And then prior probability of hypothesis 2, we have 0.35. So plus our index K now is 3. So the probability of evidence 1 given hypothesis 3, we have 0.5, and then multiplied by probability of evidence 2 given hypothesis 3. So we have 0.7, and multiplied by probability of evidence 3 given hypothesis 3, we have 0.9, and multiplied by prior probability of hypothesis 3, which is 0.25. And then if we sum the products, so if we add the products, their sum is 0.14355. So 0.0648 divided by 0.14355, the probability of hypothesis 1 given evidence 1, evidence 2, evidence 3 is equals to 0.4225. And then our I now is equals to 2. So, 2. So the probability of hypothesis 2 given evidence 1, evidence 2, and evidence 3 is equals to probability of evidence 1 given hypothesis 2. So we have 0.8. And then probability of evidence 2 given hypothesis 2, we have 0.0, and multiplied by probability of evidence 3 given hypothesis 2, we have 0.7, multiplied by prior probability hypothesis 2, which is 0.35. So if we multiply them, their product is 0. 0 divided by 0.14355. Since same process lang naman po yung sa kanina, so kinapi na lang po natin para hindi po tayo matagalan. So the probability of hypothesis 2 given evidence 1, evidence 2, and evidence 3 is equals to 0. And then our I now is equals to 3. So the probability of hypothesis 3 given evidence 1, evidence 1, evidence 3 is equals to probability of evidence 1 given hypothesis 3. So we have 0.5, and then multiplied by probability of evidence 2 given hypothesis 3 is 0.7, and multiplied by probability of evidence 3 given hypothesis 3, so 0.9, and multiplied by probability of hypothesis 3, so 0.25. If we multiply them, the product is 0.07875, and then same process lang po kanina, so we copy this one. So the probability of hypothesis 3 given evidence 1, evidence 2, and evidence 3 is equals to 0.55. So although the initial ranking was hypothesis 1, hypothesis 2, and hypothesis 3, only hypothesis 1 and hypothesis 3 remain under consideration after evidence 1, evidence 2, and evidence 3 are observed. But hypothesis 3 is now more considered likely than hypothesis 1. Bias of the Bayesian method. The framework for Bayesian reasoning requires probability values as primary inputs. The assessment of these values usually involves human judgment. However, psychological research shows that humans either cannot elicit probability values consistent with the Bayesian rules or do it badly. Burns and Pearl in 1981 and Tversky and Kahneman in 1982. This suggests that the conditional probabilities may be inconsistent with the prior probabilities given by the expert. For example, a car that does not start and make odd noises when you press the starter. The conditional probability of the starter being faulty if the car makes odd noises may be expressed as if the symptom is odd noises, then the starter is bad, with probability 0.7. Apparently, the conditional probability that the starter is not bad if the car makes odd noises is, so may ano po siya na what if hindi pala sira yung starter even when the car is making an odd noises. So the probability that the starter is not bad given the odd noises is equals to 1 minus the probability that the starter is bad given the odd noises. So kung nagtataka po kayo kung saan po nanggaling po itong 1, it represents the total probability of the two mutually exclusive events, which are the starter is bad and the starter is not bad when odd noises are observed. So The probability that starter is not bad given that add noises is equals to 1 minus 0.7, which is the probability that the symptom is add noises when then the starter is bad. So the probability the starter is not bad given the add noises is equals to 0.3. Therefore, we can obtain a companion rule that states if the symptom is add noises, then the starter is good with probability 0.3. Domain experts do not deal easily with conditional probabilities and quite often deny the very existence of the hidden implicit probability. We would use available statistical information and empirical studies to derive the following two rules. If the starter is bad, then the symptom is add noises with probability 0.85. If the starter is bad, then the symptom is not add noises with probability 0.15. So dito is nakikita po natin na there is a function not and it is represented by a symbol, this one, which is the logical function not. So to use the Bayesian rule, we still need the prior probability. The probability that the starter is bad if the car does not start. Here we need an expert judgment. Suppose the expert supplies us the value of 5%. Now we can apply the Bayesian rule to obtain. So ito po yung yung formula po or yung equation na pag may there are mutually exclusive events. For example, is the not and the not hypothesis and the hypothesis. So the probability that the starter is bad given the add noises is equals to 0.85 multiplied by 0.05. So kung nagtataka po kayo kung saan po galing itong mga values na ito, so this 0.85, so this 0.85 represents that if the starter is bad, then the symptom is add noises. And this 0.05 is the prior probability that the starter is bad if the car does not start. And then this 0.15 is the starter is bad, then the symptom is not add noises. And this 0.95 comes from the probability that we will not observe add noises if the starter is bad. So if we multiply 0.85 by 0.05, their product is 0.0425. And if we sum this, so if we sum the product of these values, so their sum is 0.185. So the probability the starter is bad given the add noises is 0.23. The number obtained is significantly lower than the expert's estimate of 0.7 given at the beginning. Certainty factors, theory, and evidential reasoning. Certainty factors theory is a popular alternative to Bayesian reasoning. Bakit po siya naging popular alternative? Because it is simpler to understand even for people with no background in probability. More robust to uncertainty and more suitable for experts because it is less computationally expensive. So basically, certainty factor theory was initially introduced as part of the Bayesian expert system. Bayesian was designed to diagnose and recommend therapies for blood infections and meningitis. In medical expert diagnosis, experts often express their beliefs or confidence in diagnosis in ways that are not strictly logical or mathematically consistent. So a certainty factor, CF, a number to measure the expert's belief, the maximum value of the certainty factor was positive 1, definitely true, and the minimum negative 1, definitely false. A positive value represented, so ang positive value po daw is represented a degree of belief and a negative value, so a negative value, a degree of disbelief. For example, if the expert stated that some evidence was almost certainly true, so ang certainty factor value nito of 0.8 would be assigned to this evidence. So kagaya po kanina, 0.8, so it is almost certainly. So this table 3.4 shows the uncertain terms and their interpretation based on the Bayesian expert systems. So, in expert system with certainty factors, the knowledge base consists of a set of rules that have the following syntax. If evidence, then hypothesis with certainty factor, where certainty factor or CF represents belief in hypothesis H, given that evidence E has occurred. The certainty factors theory is based on two functions, which are the measure of belief and the measure of disbelief. So for the measure of belief of hypothesis given evidence, so if the prior probability of hypothesis is equals to 1, it means that you're absolutely certain that the hypothesis is true, then the function returns 1. Otherwise, it would take the maximum of the probability of hypothesis given evidence and prior probability hypothesis minus the prior probability of hypothesis. So for example, the value of probability of hypothesis given evidence is 1 and the prior probability of hypothesis is 0. So their maximum is 1 minus whatever the value of the prior probability of hypothesis. And then the measure of disbelief of hypothesis given evidence is equals to, so if the prior probability of hypothesis is equals to 0, it means that you're absolutely certain that the hypothesis is false, then it would return 1. Otherwise, it would take the minimum value of the probability of hypothesis given evidence and prior probability of hypothesis minus prior probability of hypothesis. So for example, the value of probability of hypothesis given evidence is 1, and then the prior probability is 0. So their minimum is 0. So 0 minus whatever the value, where probability of hypothesis is the prior probability of hypothesis H being true, and probability of hypothesis given evidence is the probability that hypothesis H is true given evidence E. Then the values of measure of belief of hypothesis given evidence and measure of disbelief given of hypothesis given evidence range between 0 and 1. The strength of belief or disbelief in hypothesis H depends on the kind of evidence E observed. Some facts may increase the strength of belief, but some increase the strength of disbelief. So in other words, the output of these functions falls within the range 0 and 1. This range is often used in probabilistic context to represent degrees of belief or confidence, where 0 means complete certainty that something is false, and 1 means complete belief that something is true. So to determine the total strength of belief or disbelief in hypothesis, the measure of belief and measure of disbelief are combined into one equation, which is the certainty factor. So this one. So consider a simple rule. If A is X, then B is Y. An expert may not be absolutely certain that this rule holds. Also, suppose it has been observed that in some cases, even when the if part of the rule is satisfied, an object A based on value X, object B can acquire some different value Z. So it says that the expert is not absolutely certain that this rule always holds. In other words, there is a chance that even if object A is X, object B could be Z instead of Y. The expert can associate a certainty factor with each possible value of B, given that A has value of X. In this case, the certainty factor of B for being Y is 0.7, while B being Z is 0.2. So, if i-compute po natin 0.7 plus 0.2, di ba 0.9 lang po. So, where is the other 10%? The other 10% of the time, it could be anything. In such a way, the expert might reserve a possibility that object B can take not only two known values, Y and Z, but also some other values that has not yet been observed. So, the certainty factor assigned by a rule is then propagated through the reasoning chain. Propagation of the certainty factors involves establishing the net certainty of the rule consequent when the evidence in the rule antecedent is uncertain. So, for the single antecedent, you can use this equation where the certainty factor of hypothesis given evidence is equals to the certainty factor of evidence multiplied by the certainty factor. So example, if the sky is clear, then the forecast is sunny with a certainty factor of 0.8. And the certainty factor of the evidence, which is the sky is clear, is 0.5. So certainty factor of hypothesis given evidence is equals to 0.5 multiplied by 0.8. So certainty factor of hypothesis given evidence is equals to 0.4. So the result 0.4 according to table 3.4 would be read as it may be sunny. So kung natatandaan po natin based on the previous discussion that the rule can have multiple antecedents, which are the and, which is the conjunction, and the or, which is the disjunction. So for conjunctive rules, the certainty of hypothesis H is established as follows. So certainty factor of hypothesis H given evidence 1 and evidence 2 and evidence N is equals to the minimum of the certainty factor of evidence 1, certainty factor evidence 2, and certainty factor evidence N multiplied by certainty factor. So for example, if the sky is clear and the forecast is sunny, then the action is wear sunglasses with certainty factor 0.8. And the certainty of sky is clear is 0.9 and the certainty of the forecast is sunny is 0.7. Then, so the certainty factor of hypothesis given evidence 1 and evidence 2 is equals to the minimum of the certainty factor of evidence 1, which is the sky is clear. So it has a certainty factor of 0.9 and the certainty factor of the evidence 2, which is the forecast is sunny, is 0.7 multiplied by the certainty factor, which is 0.8. So the minimum between the two certainty factors of the evidences is 0.7. So we would take this one. So 0.7 multiplied by 0.8. So the certainty factor of the hypothesis given evidence 1 and evidence 2 is 0.56. The result 0.56 according to table 3.4. This conclusion might be interpreted as probably it would be a good idea to wear sunglasses today. For disjunctive rules, which are the or, so the certainty of the hypothesis H is established as follows. So the certainty factor of hypothesis given evidence 1 or evidence 2 or evidence N is equals to the maximum of the certainty factor of evidence 1, certainty factor evidence 2, certainty factors evidence N multiplied by certainty factor. For example, if the sky is overcast or the forecast is rain, then the action is take umbrella with certainty factor 0.9. And the certainty of sky is overcast is 0.6, and the certainty of the forecast is rain is 0.8. Then, certainty factor of hypothesis given evidence 1 or evidence 2 is equals to the maximum of certainty factor of evidence 1, which in this case is the sky is overcast, is 0.6, and the certainty factor of the forecast is rain is 0.8, multiplied by the certainty factor, which is 0.9. The maximum certainty factor of the two evidences is 0.8. So we'll take this one. 0.8 multiplied by 0.9. So the certainty factor of hypothesis given evidence 1 or evidence 2 is 0.72. The result 0.72 according to table 3.4, which can be interpreted as almost certainly an umbrella should be taken today. When the same consequent is obtained as a result of the execution of two or more rules, the individual certainty factors of these rules must be merged to give a combined certainty factor for a hypothesis. Suppose the knowledge base consists of the following rules. So for rule 1, if A is X, then C is Z with certainty factor 0.8. And rule 2, if B is Y, then C is C with certainty factor 0.6. Certainty should be assigned to object C having value Z if both rule 1 and rule 2 are fired. So sometimes, two or even more rules can affect the same hypothesis. So how does an expert system cope up with such situation? If we have two pieces of evidence, A is X and B is Y from different sources, Rule 1 and Rule 2 supporting the same hypothesis, C is Z. Then the confidence in this hypothesis should increase and become stronger than if only one piece of evidence had been obtained. So, ang ibig mong sabihin nito is, if i-combine po natin yung dalawang hypothesis, then it should increase and become stronger. So, to calculate a combined certainty factor, we can use the following equation. So, for the first equation, if the evidence is used when both pieces of the evidence are positive. So, the certainty factor of the combined evidences is equals to the sum of the certainty factor of the two pieces of evidence multiplied by 1 minus certainty factor. And then for the second equation, it is used when one or both pieces of evidence are negative. In this case, the certainty factor of the combined evidence is equals to the sum of the certainty factor of the two pieces of evidence divided by 1 minus the minimum of the absolute values of the two certainty factors. And then for the third equation, it is used when both pieces of the evidence are negative. So the certainty factor of the combined evidence is equals to the sum of the certainty factor of the two pieces of evidence multiplied by 1 plus certainty factor, where certainty factor 1 is the confidence in hypothesis H established by Rule 1. Certainty factor 2 is the confidence in hypothesis H established by Rule 2, and absolute certainty factor 1 and absolute certainty factor 2 are absolute magnitudes of certainty factor 1 and certainty factor 2 respectively. So thus, if we assume that certainty factor evidence 1 and certainty factor evidence 2 is equals to 1, so both positive siya. So ang gagamitin po natin is this one. So, then from the equation, certainty factor, so kung natatandaan po natin is the single antecedent. So, certainty factor of hypothesis given evidence is equals to certainty factor of evidence multiplied by certainty factor. So, for the certainty factor 1 of hypothesis given evidence 1, so since positive 1 po siya, then multiplied by 0.8, which is the certainty factor 1. So, 0.8. And then certainty factor 2 of hypothesis given evidence 2 is equals to 0.6. So then from the equation, so gagamitin po natin yung first equation kasi po both positive po yung two evidences. So the certainty factor of the combined evidence is equals to certainty factor 1 of hypothesis given evidence 1, which is 0.8, and then plus certainty factor 2 of hypothesis evidence 2, which is 0.6, multiplied by 1 minus certainty factor 1 of hypothesis given evidence 1, which is 0.8. So 0.8 plus 0.6 and then multiplied by 1 minus 0.8. So the combined evidence, the certainty factor of the combined evidence is equals to 0.92. And it shows that there is an incremental increase of belief in hypothesis and also confirmed the expectations nung isa natin yung dalawang evidences. So, we will now consider a case when rule certainty factors have the opposite sign. So, kasi opposite sign siya, so yung ikalawang equation yung gagamitin natin. So suppose that certainty factor of evidence 1 is 1 and the certainty factor 2 is negative 1. So then from the equation, so same lang yung gagawin natin. So certainty factor 1 of hypothesis given evidence 1 is equals to 1. So yung certainty factor ng evidence 1 is 1 multiplied by 0.8, so we have 0.8. And then certainty factor of hypothesis evidence 2, and then the certainty factor, given certainty factor of evidence 2 is negative 1, and then multiplied by certainty factor 2, so 0.6, so negative 1 multiplied by 0.6, so we have negative 6. So from the second equation, we have the certainty factor of the combined evidence is equals to certainty factor 1 of hypothesis given evidence 1. So we have 0.8. And then plus, so since the certainty factor 2 of hypothesis given evidence 2 is negative. So, we have different signs. So, minus talaga siya. So, 0.8 minus 0.6. So, we have 0.2. And then 1 minus the minimum of the absolute values of the two certainty factors. So, 1 minus, so nakikita po natin dito na ang the value of certainty factor 1 of hypothesis given evidence 1 is 0.8. And then absolute value, so certainty factor 2 of hypothesis evidence 2, di ba negative 0.6 siya. Kasi kaya po siya naging positive because of absolute value. Kaya 1 minus minimum of 0.8 and 0.6. So, ang minimum value po dito is 0.6. So, the certainty factor of the combined evidences is 0.5. So, it shows how a combined certainty factor, or in other words, net belief, is obtained with one rule, which is the rule 1 confirms the hypothesis, but another rule 2 discounts it. So, we'll consider now a case when rule certainty factors have negative signs. So, parehang negative signs yung dalawang evidences. Then, from the equation, certainty factor of hypothesis given evidence is equal to certainty factor of evidence multiplied by certainty factor we get. So, certainty factor 1 of hypothesis given evidence is negative 0.8, and the certainty factor of hypothesis given evidence 2 is 0.6. So, dito is the certainty factor of the combined evidences is equals to certainty factor 1 of hypothesis given evidence 1, and its value is negative 0.8. And then plus, so since ang certainty factor 2 of hypothesis given evidence 2 is negative, so different sign siya, so minus na. So we will subtract it. So negative 0.8 minus 0.6 multiplied by 1, and then plus certainty factor 1 of hypothesis given evidence 1. So since ipa-plus natin siya or i-add, and then yung value ng certainty factor 1 and of hypothesis given evidence 1 is negative, so we will subtract it. So the value of certainty factor of the combined evidences when both of the evidences are negative is equals to negative 0.92, and it represents that there is an incremental increase of disbelief in hypothesis. So the certainty factors theory provides a practical alternative to Bayesian reasoning. The heuristic manner of combining certainty factors is different from the manner in which they would be combined if they were probabilities. The certainty theory is not mathematically pure, but does mimic the thinking process of a human experts. So application. Expert systems designed for medical purposes have been an integral part of the historical development of artificial intelligence expert systems. One of the earliest expert programs developed using LISP processing or LISP was a psychotherapist program named Doctor. As research continued, particularly at Stanford University and the Massachusetts Institute of Technology or MIT, further rule-based systems were developed. At Stanford, an expert system called MySyn was developed to diagnose blood and brain infections and to recommend appropriate therapy, a system which provides to be as nearly as accurate as human physician. The inference engine from MySyn, the essential MySyn, was used to develop many new expert systems. The root of most of today's medical expert systems are derived from MySyn, CASNet Glaucoma Diagnostic System and Internist, according to Robertson, 2023. MySyn is a rule-based expert system that uses certainty factors to represent the degree of belief in the rules and the evidence. The certainty factors are propagated through the rule base using a backward chaining approach. MySyn starts with the hypothesis and then tries to find evidence that supports the hypothesis. The certainty factors are used to determine which rules are applicable and how much weight to give to each rule. The final certainty factor for the hypothesis is the product of the certainty factors of the rule that support the hypothesis. So here are some of the steps involved in uncertainty management in MyScene. Knowledge acquisition. The knowledge base is created by interviewing experts and collecting medical literature. The knowledge base consists of rules and facts. Rule evaluation. The certainty factors of the rules are assigned by the experts. The certainty factors represent the degree of belief in the rules. Evidence gathering. The evidence is gathered from the patient. The evidence can be in the form of symptoms, laboratory tests, and other medical tests. Rule application. The rules are applied to the evidence to determine the certainty factors of the hypothesis. Diagnosis. The hypothesis with the highest certainty factor is the diagnosis. So this is the MyScene expert system. So this is how it works. So from the users, so the user of the system can be a doctor or other healthcare professionals. And then it will add a query or questions. Then the user's interface, it allows the user to interact with the system and enter information about the patient, such as their symptom test, result, and medical history. Then the inference engine, so it uses the knowledge base to reason out about the patient's symptoms and test result and to arrive at the diagnosis and treatment recommendation. And then the knowledge base, it contains the knowledge that the systems uses to make its decision. And then after that is it would generate an advice. So the system provides advice to the user on the diagnosis and treatment of the patient. So that's all and thank you for listening.